Hi everyone. In this section 5.5, we are talking about counting. We're going to learn how to count today, which is actually kind of exciting. I like this part of the course quite a bit. So we're going to learn what is a factorial. We're going to learn what is a binomial coefficient. We're going to learn what is a permutation, what is a combination, and we're going to learn how to count. And, counting is really a topic in mathematics, believe it or not. So a lot of research there. And we're only going to learn the very basics of counting today. So sort of getting your feet wet for how to count objects. Now, suppose you attend your friend's wedding, and at the reception, you get one choice out of two possible appetizers. You can choose either a soup or a salad. You get one choice out of three possible entrees, so you can get a steak, chicken, or fish for your entree. You can get also one out of three desserts, so you can choose pie, cake, or pudding for dessert. The question is, how many unique meals can be created from these choices available to you, right? Well, here's one way you can do this. And I think this is how most students begin if you see this and you don't know what to do, right? You say, well, let's start with appetizers. I can have either soup or salad for my appetizer. That's where we start. We choose one of those. And regardless of whether I choose soup or salad, I can choose for my entree, I can choose either steak, chicken, or fish. If I choose a soup, I can choose steak, chicken, or fish. And if I choose a salad, I can choose steak, chicken, or fish, right? Like this. And then for my dessert choice, regardless of the two choices I've made before, I can choose either pie, cake, or pudding. I'll number these 1, 2, or 3. And so even if I choose soup and steak, I can still choose pie, cake, or pudding. And if I choose soup and chicken, I can still choose pie, cake, or pudding. And if I choose soup and fish, I can still choose pie, cake, or pudding. And I'm running out of room over here, but if I choose salad and steak, I still have my three choices of dessert. If I choose salad and chicken, again, three choices of dessert. And if I choose salad and fish, I still have three choices for dessert. So this is messy the way I've written it, because I forced myself out of the room I could have utilized on the slide. But this is what we call a decision tree, right? So this little tree here has, a bunch of different leaves, and each branch branches off into many different things. But it allows me to count the number of unique meals I could create, right? I just have to count up the number of leaves on my tree. So let's count. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 choices. There are 18 choices on my decision tree. So there's 18 unique meals. That's my answer. But I'll give you a little bit of a, hint here, or a little bit of a secret if you haven't seen it already. All I'm doing here is saying two choices of appetizer times three choices of entree times three choices of dessert. Well, 2 times 3 is 6, and 6 times 3 is 18. So that's a much easier way to arrive at your answer without having to draw a decision tree. So now, if I ask you this question, suppose you drive up to Sonic and you want to order a drink, but you have 10 different sodas to choose from at Sonic. And ice-wise, you could either have no ice, normal ice, or I always ask for light ice. That's just being a little bit extra, but I don't want my whole cup to be filled up with ice. And you have one choice out of 4 syrups, right? So you could have no syrup in your drink, or you could ask them to add a cherry syrup, a vanilla syrup, or a lime syrup. And then you have sizes of drinks, right? So we have a small, medium, large for our size choices. And so now we ask how many unique drinks can be created from these choices. Well, this is 10 sodas times 3 choices for ice times 4 choices for syrup times 3 choices for size. And 3 times 4 would be 12, and 12 times 3 would be 36, and 36 times 10 is 360 for my final answer here. So, knowing that you can just multiply through by these independent choices is helpful, because drawing a decision tree would be a nightmare for this situation, right? So let's think about a new situation. You're a traveling salesman, and you have to drive to 5 different cities this week to do your job. Now, you're in charge of your own schedule, so you can put those 5 cities in any order that you want, right? Here's the question. How many different ways can you put 5 different cities in order, right? So to decide your schedule for this week, you've got to come up with an order in which you're going to visit each city. But how many different ways can you do that? I encourage you to pause this video and think about it and come up with an answer, right? I want you to think about this before you just see the solution. And now I'm going to assume you've come up with your own answer, and now you're just ready to check to see if you were correct. But here's what we're going to do. We're going to see the first city, whatever we visit, and then the second city, and then the third city, and then the fourth city, and then the fifth city, right? How many choices do we have for each of these? So for the first city, I actually have 5 choices. I have 5 cities that I could potentially visit as my first city. But now after I've visited that first city, I actually only have 4 choices for my second city. And after I've seen the first 2 cities, there's only 3 cities remaining that might be the third city I visit. 2 choices for my fourth city. And now after I've already visited the first 4 cities, there's only 1 city remaining. There's only 1 possibility that could be my last city. Now 5 times 4 times 3 times 2 times 1. Times 1 doesn't really matter, but 2 times 3 is 6. 4 times 6 is 24, and 24 times 5 is 120. So this is our answer here for that type of problem. Okay. So now imagine that you are going to be a judge at a chili cook-off event. And so a chili cook-off is where competitors cook a chili and they present their chili to the judge. And, as a judge or serving on a panel of judges, you have to rank the chilies in order of the one you like the most to the one you like the least. And so just as a point of curiosity, maybe you think to yourself, how many different ways could I fill out my scorecard, right? Well, same as before. For your favorite chili, you have 7 options. And your second favorite, that means you have 6 options. And then for your third favorite, you have 5 options. And we just do this. And then by the time you're choosing your least favorite chili, there's only 1 chili left to rank. And so this is the same idea. So remember, 5 times 4 times 3 times 2 times 1 from the last slide was 120. Now 120 times 6 is going to be 600 plus 20 times 6, and 20 times 6 is going to be 120, right? So that's 720. If I pop that 6 in, this now becomes 720. Okay. So that's not the question, though. We're asking 7 times that. So we're talking about 7 times 720. 7 times 7 is 49. And then 7 times 20 would be 140. So this is going to be like 5,040. There we go. Final answer. There's actually 5,040 ways you could fill out your scorecard. And to me, that's surprising. That's like a lot of different possibilities, right? For just ranking 7 different items. Kind of neat. What we've been doing is actually called the factorial, because this type of problem where you put things in order, that type of problem shows up a lot in mathematics. And so we've actually given it a name, and the notation we use for the factorial is an exclamation mark. And so what we were just doing with the chilies, when we put 7 chilies in order, that is called 7 factorial, and this is how you represent it. Now, let's say that your rock band is on tour. So you're going to visit 35 different cities while you're on tour, and you're wondering to yourself, out of 35 cities, how many different ways could I visit 35 cities, right? Putting them in different orders. Well, this answer to the question would be 35 factorial, because we know we're just putting, cities in different orders. So if we pull out our calculator here, you might be interested in what is 35 factorial. And I'll be honest with you, I don't remember exactly where this is, but I think it's under the math button. And maybe going to number. We'll see if it's somewhere on this list. Okay, it's not. So we're going to go to probability. My calculator is frozen. Okay, let me restart that. Okay, trying that again. We go to math, we go over to probability on the top here, and then we go down to number 4, where we have that exclamation mark. That puts in a factorial. And what we want is 35 factorial. So we'll put that in really quick. So 35 factorial is this. It's a 1 followed by 40 zeros. It's a 1 followed by 40 zeros. So it's like 1, then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Continue on the next line. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so 1 followed by 40 zeros. That's a large number. Okay, new example. Suppose that you have a toddler, and your toddler is playing with blocks. And there are 5 unique blocks. So we have a red, blue, green, orange, and purple block. And now, since your toddler has only 2 tiny little hands, let's say your toddler can only hold 2 blocks at a time. And you wonder to yourself, how many different ways can my toddler choose 2 out of the 5 blocks to hold? And notice in this question, order does not matter here. We're only saying if you've got 5 distinct blocks and you pick up 2 of them, how many different ways can that happen? And this is a point where I invite you to pause the video and think about this question for yourself. Please come up with a solution and have that ready so that you can check your answer, because this is the best way to learn really is trying things on your own. And at this point, I'm going to move on, assuming that you've done that and you've given it your best shot. So my answer to you is to say, well, if we pick up the red block first, and there's 4 other options, right? And then we pick up the blue block first, and there's 3 other options if I don't count picking up the red block. And I wouldn't, because I've actually already counted the red-blue pair when I wrote down this 4. So if blue is first, there's 3 other options. And if green is first, there's 2 other options. And if orange and purple is the last pair that I haven't counted. And so in this case, I'm actually looking at 10 possibilities. And when we talk about this particular situation where we have 5 items and we choose 2 of them, we call this 5 choose 2. Okay, so this is the introductory example. But new example, suppose that you're a judge on American Idol and there's 100 contestants in the first round. Now only 10 of those contestants can go to Hollywood. If you haven't seen American Idol before, it's kind of an old show. The second round always took place in Hollywood, and so if you successfully passed the first round, they tell you you're going to Hollywood. But basically, the question now is how many different ways can you choose 10 out of the 100 contestants? So order doesn't matter, by the way, right? So we're not ranking the contestants. But what we do have is we have 100 distinct or unique contestants, and I want to be able to choose 10 out of them. How many different ways can we do that? Well, in this case, we would say we're talking about 100 choose 10. And that is a lot more difficult to think about, just as a question. So what we do is we say, well, we come up with a name for it, and we call it the binomial coefficient. And so because this problem comes up so many times, the number of different ways you can make a selection, again, we have a name for it. It's called the binomial coefficient. And the way we write this, if we have n choose k, is we write n on top of k like this, and then we write the parentheses around it. Careful not to put any kind of bar here, because that's just the fraction n divided by k. But if we want the binomial coefficient n choose k, this is how we write it. So in our case with American Idol, but like before, we have 100 choose 10. And in our case with the toddler holding the blocks, we had 5 choose 2. So at least know 5 choose 2 has to be 10. And we can use that to check our little formula right here. So for 5 choose 2, my formula in the green box tells me that this must be 5 factorial divided by 2 factorial times 5 minus 2 factorial, right? So let's see if this works out. That's going to be 5 factorial divided by 2 factorial times 3 factorial. Now the idea behind the factorial is that 5 factorial will look like 5 times 4 times 3 times 2 times 1. 2 factorial would be 2 times 1, and 3 factorial would be 3 times 2 times 1, right? Now notice I don't have to write times 1, and you might see me just ignore the times 1 in the end, because multiplying by 1 doesn't really do anything, right? Also, if I have 3 as a factor in the numerator and denominator, I can cancel that, and same thing with the 2. Now, I'm left with 5 times 4 divided by 2, and I might just say that, let me cancel that 2 in the denominator and let that 4 now be 4 divided by 2, which is 2. Now 5 times 2 is 10, and that checks out with what we reasoned about before. However, this formula is actually going to help us with that American Idol problem, because we decided this was just too difficult to think about, without actually employing sort of this formula. And so we have 100 choose 10. Oops, I made that mistake. There we go. 100 choose 10. Well, my formula says this is 100 factorial divided by 10 factorial times 100 minus 10 factorial. Okay, so now 100 factorial is going to be, 100 times 99 times 98 and so on, times 3 times 2 times 1, all the numbers in between included as well. 10 factorial is just going to be 10 times 9 times 8 times 7 and so on, down 2 times 1. And lastly, 100 minus 10 is just 90 factorial, so that's 90 times 89 times 88 times 87 and so on, all the way down until you multiply by 1. Okay. Now a lot of things are going to simplify here. Like at a certain point in 100 factorial, you're going to do 100 times 99 times 98 times 97 times 96 times 95 times 94 times 93 times 92 times 91 times, well, 90 factorial, because 90 factorial is making it the rest of the way down. So I can actually cancel out this 90 factorial with all of the stuff that happens between 90 and 1 right here. So I've made a little bit of a simplification. So let me write out what I'm left with after I cancel out that 90 factorial from the denominator. I have 100 times all of this stuff. And I know it's still pretty large. Times this stuff. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay. Now this is still pretty crazy, but I want to point out that you probably could do this if you were stranded on a desert island without a calculator, right? So these zeros and the 10 and the 100 cancel, and so I'm just left with a 1 there, and I can, 100 divided by 10 is just 10. 99 divided by 9, well, that's actually just 11, isn't it? And 98 divided by 2 would just be 49. If I cancel the 2, 1 doesn't matter. 96, I can divide 96 by 3, and that's just 32, right? 95 divided by 5, that's 19, isn't it? And just, these are just ideas, right? So I'm not saying you have to calculate this by hand, because again, it's still pretty crazy, but there's simplifications to it. It's not just all madness. Okay. This being a pretty crazy thing, we'll just put it in the calculator and see what happens. So let's do 100 times 99 times 98 times 97 times 96 times 95 times 94 times 93 times 2. That number divided by 10 factorial, right? And the answer to our question is about 1.7 times 10 to the power 13. So that's pretty close to 2 with 13 zeros behind it. Basically a really huge number. I'll go ahead and write it there. 1.73 times 10 to the 13th power. Okay. Now suppose we have a new situation where you are eating at Genghis Grill, which is just sort of a buffet style restaurant where you get a big bowl and you just pick out things as you go down, the line, and you have a bunch of options to choose from. So for your protein choice, there's 8 different types of protein. Maybe they have like a couple different types of fish, they have steak, they have chicken, they have pork, maybe tofu, soybeans, I don't know, some other stuff going on in there. So 8 different types of protein. You can only choose 3 of those actually to go into your bowl. So they limit you. They won't let you choose all 8 proteins to go into your bowl, but they only make you choose 3 out of 8. And so this would be a situation where we have 8 choose 3. So for the binomial coefficient, we write 8 over 3 like that. Now this will be 8 factorial divided by 3 factorial times 8 minus 3 factorial. And so remember, 8 factorial will be 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And 3 factorial will be 3 times 2 times 1. And 8 minus 3 is, of course, 5. So 5 factorial is 5 times 4 times 3 times 2 times 1. Now, this is going to be a lot better example, but what I'm showing you is ones don't matter. These 2's in the numerator and denominator simplify, along with 3, 4, and 5. And 8 divided by 2 is just 4. So let me write up here. 8 divided by 2 is 4, so I can cancel out that 2. And then I have times 7, and then times 6 over 3. Well, 6 divided by 3 is just 2. So now this is 8 times 4 times 2, 7 times 4 times 2, which is 7 times 8, which is 56. So that you can actually do without a calculator. Not too bad. Here is a new situation, brand new. So we can't actually use the binomial coefficient alone to solve this question. But here we go. Pause the video, please, and give it your best shot. And now I'm going to continue, assuming you've already made your best attempt to answer this question. And what it says is, someone comes up to you and asks you, what are your top 3 favorite Power Rangers? And of course, there's 6 options that might be in the top 3, right? So order actually matters now for your top 3. They want to know what is your favorite, what is your second favorite, and what is your third favorite Power Ranger. But order doesn't matter for those ones that you're not going to be stating in your response, right? So when you ask how many different ways can you respond, we're talking about picking 3 out of them and then putting those 3 in order. Now notice, this is going to be 6, choose 3, to pick 3 out of the 6. But that's not putting them in order yet. And so then what we're going to do is multiply times 3 factorial, right? Because how many different ways can you put 3 Power Rangers in order? We've actually addressed that question earlier in this video. So this will be 6 choose 3 times 3 factorial. Now 6 choose 3 is going to be 6 factorial divided by 3 factorial times 6 minus 3 factorial, which is going to be then 6 factorial over 3 factorial times 3 factorial. Oops. And then I forgot to multiply by this 3 factorial, so don't make the same mistake as me and actually remember, multiply by that 3 factorial. Oops. Times 3 factorial. Okay, so that one actually, this guy out here is going to cancel with the one of those in the denominator, and I get 6 factorial over 3 factorial. And that is going to cancel out 3, 2, 1, and so I get is 6 times 5 times 4, and 6 times 5 times 4, that will be 6 times 20, which is 120. Final answer. So, the number of different ways you can tell someone what your top 3 favorite Power Rangers are in order, that's 120. Oh, and here, in the rest of the slides, I've walked you through this up. So, I guess in a different situation, where maybe there's an extra Power Ranger, and you barely see him, because I think the other Power Ranger I was thinking of last year when I wrote these notes was the White Ranger. I think the White Ranger appears in maybe some Power Rangers movies. So imagine there's another extra Power Ranger. We're going to choose 3 out of 7, right? And the way to choose 3 out of 7 is 7 choose 3 binomial coefficient. We're going to put those 3 in order, and the way to do that is 3 factorial. And again, we get the same sort of formula we came up with. But to speak more abstractly, if you have k items, if you have n items, and then we choose k, and then we put them in order, in other words, we have an arrangement, this is how you do it. You do n choose k times k factorial. And now actually expanding out that formula for n choose k, we'll notice there's always a k factorial in the denominator, and so when we cancel out those k factorials, this is the formula for what we call permutations with distinct items. And so a permutation being I'm going to choose k items and place them in order out of in total items. So similar, we say rank your top 5 NFL QBs. So we're talking about starting quarterbacks only. How many unique responses are possible? Well, judge me if I get this wrong, but I think there's 32 teams in the NFL. So there would be 32 starting quarterbacks. And so if we were going to choose 5 and rank them, it's going to be 32 choose 5 times 5 factorial, which again, this should be a permutation of distinct items. And so this is going to be then 32 factorial divided by 32 minus 5 factorial. Okay. Arranging t-shirts. So suppose that you now have 3 identical white t-shirts, 2 identical red t-shirts, and 2 identical blue t-shirts. Now, how many significantly different ways can you wear all of these t-shirts during the course of a week? Notice that there's 7 total. So each day of the week you're going to wear 1 t-shirt. You're not going to wear it again for the same t-shirt. But for each white t-shirt, you can't tell the difference between them. And for each red and blue t-shirt, respectively, you can't tell the difference between the red t-shirts and you can't tell the difference between the blue t-shirts. So whenever I ask how many significantly different ways, we're saying that these t-shirts, they're not distinct from each other. And this makes more of an interesting question. You won't be able to use the formulas we've discussed earlier in the video, but I want you to pause the video now, try to figure this question out. Like legitimately try to figure this out and get the correct answer before I tell you the solution. Because I think it's an important exercise and it's worth your time. Now I'm going to move on and sort of show you the solution to this arranging t-shirts problem. And the way I like to think about this is to say, what if I pretend that these are all unique? Let's pretend for a moment that these are distinct t-shirts. In this case, if I wanted to put them in order, and putting them in order is the same as deciding which day of the week you're going to wear them on, if we pretend they're distinct, we're talking about 7 factorial different ways you can put those t-shirts in order. However, I'm going to remove 2 factorial because, there's these 2 red shirts and I can't even tell the difference anyways. And then I'm also going to remove 2 factorial because there's these 2 blue shirts and I, don't really care which order I put those 2 shirts in. So I'm going to remove 2 factorial because that's part of, the part in order I don't care about. And then I'm also going to remove 3 factorial because, heck, I don't care the order that those white shirts appear among the white shirts. And so my resulting formula is going to be this. It's going to be 7 factorial, but then divided by 3 factorial, 2 factorial, and 2 factorial. I'm dividing by those factorials because as far as white shirts, among the white shirts, I don't care what order the white shirt comes in. Those are not distinct among themselves. So anyways, the answer, and I sort of didn't give myself enough room here. I'll write it down here, I suppose, is 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 3 times 2 times 1 times 2 times 1 times 2 times 1. So the 1s don't actually matter. I could have just omitted 1s. 2s cancel here. 4 over 2 is just 2. 6 over 2 is just 3, and then the 3's cancel. So I end up with 7 times 3 times 5 times 2, and everything else is canceled. So 5 times 2 is 10, 7 times 3 is 21, so this is 210, final answer. This is what we call permutations with non-distinct items. So this n up top is going to be the total number of items, and then each subscript is referring to a subgroup. So N1 is the subgroup. Just like before with the t-shirts, maybe you can see where we're coming from. The overall order kind of matters, but the order of the subgroup doesn't matter. That's how we come up with this formula. So now let's say you want to make a stylish border in your bathroom. So you've got tiles along the wall. And this is what you have. You have 4 brown tiles, 5 blue tiles, and 6 green tiles. Okay, this is what we have. And we're going to place these in order. How many significantly different ways can you place these tiles in order? Well, how many total do we have? We have 15 total. Pause the video now and try to solve this. I'm moving on assuming you've given it a good shot, because if you're not actually trying these examples, it's not going to stick with you as much. It's good practice to actually attempt. So the answer here is going to be 15 factorial divided by 4 factorial times 5 factorial times 6 factorial. Okay. Now, let's say we're shuffling cards, and you have a standard deck of playing cards with 52 cards, and you shuffle that deck really well. What is the probability that the cards are in the same order in which they came? Exactly the same order that they came in, right? So if we shuffle really well, that means the first card that is on top of the deck has 1 of 52, and the next card on top of the deck is 1 out of 51, and the next card that's out of the deck has 50 possibilities, and the fourth card has 49 possibilities, and so on, until the last card in the deck is really already decided by the first 51 cards. So there's only one possibility there. This is actually 52 factorial. Different possibilities for the different ways that you might be ordering these cards. And in shuffling, we don't really know. It's kind of a random process. And if there's 52 possibilities, each with equal probability, then the probability that they are in the same order that they were in before you shuffled, we'll call that E1, I guess, for that event. Well, that's going to be 1 out of 52 factorial. And so I mention this because, I mention this because I want to show you the link, I guess, between counting and probabilities. So a lot of times whenever you're asked about a certain probability, it sort of requires a counting problem first to determine how many, distinct possibilities there are. And then whenever you ask the probability question, most of the time it'll be like 1 over the number of possibilities. But in some cases it's a little bit different. So of course, be careful when you're reading questions. All right, that's it for this video, and I hope you have a good rest of your week.